This project analyzes a gym cable pulley mechanism commonly used in resistance training. The weight stack moves vertically while the pulley rotates about a fixed axis. Because the cable does not slip, linear and angular motions are linked using kinematic relationships. Newton's second law is applied in both translation and rotation to analyze the system dynamics. The objective of this project is to study the motion of a J-pulley system by applying both kinematics and kinetics. We analyze the translation of the weight stack and the rotation of the pulley, then apply Newton's second law to determine acceleration and cable tension. Our case study is a jib cable pulley mechanism used in resistance training machines. When the user pulls the cable, the pulley rotates about a fixed axis and the weight stack moves vertically. Because there is no slip, linear and angular motions are coupled, allowing us to apply Newton's second law in both translation and rotation to solve for acceleration and cable tension.
Methodology. First, we want to look about assumptions. To simplify the analysis of the zinc cable pulley mechanism, several ideal assumptions are made. The cable is considered massless and inextensible, ensuring uniform tension throughout the system without stretching. The pulley is treated as a rigid body that rotates freely with a negligible friction at the axle and no slipping occurs between the cable and the pulley, allowing a direct relationship between the linear motion of the cable and the angular motion of the pulley. The pulley is assumed to have either negligible mass or non-constant moment of inertia. The weight stack is constrained to move only in the vertical direction. While air resistance is neglected, gravitational acceleration is taken as constant at gravity equals to 9.81 meter per second. Additionally, the user is assumed to apply a smooth and continuous pulling force, and any elastic deformation of the cable, pulley or supporting structure is neglected so that all components behave as rigid bodies. The second one would be free body diagram. This case study utilizes a Jim cable pulley mechanism to demonstrate the fundamental principles of rigid body kinematics and kinetics. The real-life physical system has been modeled into a free body diagram, allowing for the direct application of kinematic equations to analyze the relationship between the linear motion of the cable and the angular motion of pulley. Figure 2.0 illustrates the idealization process where the real-life physical system converted into a free body diagram (FBD) to facilitate dynamic analysis. Next one would be kinematic relationship. The kinematic behavior of the gym cable pulley system is governed by the direct coupling between the translational motion of the cable and weight stake and the rotational motion of the pulley. Due to the inextensible cable and the absence of slipping, the linear displacement, velocity and acceleration of the cable are directly related to the pulley's angular motion by the relationship S equals to R tangent and velocity equals to R omega and alpha A equals to R alpha. Since the cable length remains constant and any movement of the weight stake corresponds to an equal amount of cable motion at the handle. As a result, the vertical velocity and acceleration on the weight stake are equal in magnitude to the cable's linear velocity and acceleration. This kinematic constraint fully couples the translational and rotational motions, enabling the system to be analyzed using rigid body kinematics and Newton's second law. Finally, the applications of Newton's second law. The Newton's second law is applied to both translational motion of the weight stack and the rotational motion of the pulley to analyze force transmission in the Jim cable pulley system. For the weight stack, the upward cable tension and downward gravitational force determine its motion, leading to the relationship T minus mg equals to me, which shows that acceleration depends on the net force acting on the mass. For the pulley, the cable tension generates a torque Q that causes rotation, described by the rotational form of Newton's second law, T R equals to Ie. By using kinematic relationships A equals to RA, the translational and rotational equations are coupled. This demonstrates how the user's pulling force is transmitted through the cable and pulley to produce acceleration of the weight stack, providing a complete dynamic description of the system.
Hi, Assalamualaikum. My name is Muhammad Haikal bin Akil. My number metric is CD240223. So today I want to talk about calculation about Jim cable pulley, that the case study we doing. Important Jim cable pulley system parameters such as linear speed after moving, angular speed of pulley, time taken, define tension, transitional motion of weight stack, and lastly is rotational motion of a pulley are calculated in this section. So to comprehend the connection between linear motion and as well as rotation, and system motion is made apparent by the result of this computation, which also aid in comprehending how each rotate at a specific time. We were able to more precisely analyze the Jim cable pulley motion and connect in to the system force and speed by using this computation method. So we go to the calculation part. Is the given is mass of pulley is 1 kilogram, and pulley radius is 4.5 centimeter, and weight stack mass is 30 kilogram, and we apply putting force at free end of the cable is 300 newton and gravity 9.81, and displacement we using 0.5 meter. So first is we have to find the I is inertia, and we get the answer is 0.0010125 kilogram meter square, and we get to the angular acceleration, and we using the formula, and the upwards is T1 and downward is mg. So Fy equal to ma, and T1 minus mg equal to ma. So we get the answer T1 equal to 94.3 plus TTA. So next we have to calculate rotational motion of pulley. So what is rotational motion of pulley? We have to find the T1 and T2. T1 is tension 1, is T2 is tension 2. So we have to using a formula the T2 minus T1 times R equal to I initial that we have find before, and angular, and we have defined before too. So we using this formula, and we get the answer is radius is 0.002025 meter. So in this case we have to substitute T2 300 and the angular that we find before, and we have to compute and into the 300 minus T1 equal to 0.5. So solve for acceleration A, substitute to T2 and to 94.3 plus 30A into 300 minus T1 equal to 0.5A. And the last we get the answer is acceleration is 0.1869 meter per second square is upward. And the last, we have to find the tension and acceleration analysis. So we have to solve three things. Is solve for angular acceleration. So angular acceleration is that we find we have to using the formula angular equal to a acceleration and over to r radius, and we get the answer 4.153 radius per second cube per second square. And second is we have to find the tension that we have to find is tension 1 is 299.91 and tension 2 is 300 Newton. And third is linear speed after moving. So linear speed after moving, we using the formula v square v square 2as. So this is the formula, v square equal to 2as, and we get the answer 0.4323 meter per second. And the last is time taken. We have to find the time the pulley pull the cable, and we get we have to using the formula T equal V to A, and we get the answer 2.32 second. And last is angular speed of pulley. So angular speed of pulley is omega is V over R, and we get the answer 9.91 radius per second.
Hello, Assalamualaikum. My name is Muhammad Naushad bin Ahmad Najib. My meeting number is CD240269. Now, I want to explain about discussion about my case study, my group case study. Okay, for the first point about discussion is kinematic analysis. The update calculation clearly show the strong relationship between translational and rotational motion in the pulley system. The weight start move upward with a velocity of 0.432 meter per second and acceleration of 0.1869 meter per second square, while the pulley rotate with angular velocity of 9.61 radius per second and angular acceleration 4.15 radius per second square. This result confirm the kinematic constraint equation. Acceleration equal to R alpha. Alpha is angular acceleration, proving that tangential acceleration at the pulley ring matches the linear acceleration of the weight state. This ensures smooth resistance and prevent jerky motion, which essential for safe gym equipment design. Okay, for the second point is application of Newton's second law. Newton's second law was applied to both translational and rotational motion. The tension force were nearly equal with 299.91 Newton acting on the weight side and 300 Newton applied by the user. This small difference in tension was enough to generate the torque required to rotate the pulley and overcome its inertia of 0.0010125 kgm². The close balance between applied force and gravitational load show that the system is well controlled, producing safe and steady acceleration. This demonstrates how force transmission in pulley system can be explained effectively using Newton principles. Okay, for the last point is theoretical versus real life comparison. Although the theoretical model assume a frictionless pulley and a messless cable, real-life system introduce additional factors such as bearing friction, cable deformation, and variation in user pulling force. These factors slightly increase the required force and reduce acceleration. However, the theoretical prediction remain close to expect practical behavior, validating the rigid body model used in this study. This shows that simplified assumption can still provide reliable insight into system performance, while engineers must remain aware of real-world derivation. That's all for me. Thank you.
To wrap our presentations, let's look at our conclusions. This project successfully analyzed the dynamic of a gym cable pulley mechanism using fundamental principles of kinematic and kinetics. The results show a strong correlations between translational and rotational motions. The weak state linear accelerations of 0.1869 meter per second square correspond directly to the pulley angular accelerations of 4.15 radian per second square, with an angular speed of 9.61 radian per second. The tension force were nearly equals to 299.91 Newton versus 300 Newton, producing sufficient torque for smooth and controlled rotations. The study confirmed that free body diagrams and dynamic equations F equal to ma, tau equal to inertia versus accelerations, angular accelerations can accurately model system behavior, validating the efficiency and safety of the pulley design, while real-world factors such as frictions and cable deformations may slightly affect performance. The theoretical model remains reliable. Overall, this case study demonstrates how dynamic principles translate into practical engineering applications, ensuring safe and effective gym equipment design.